Welcome everybody. We have a special presenter today at today's Rubin Science Assembly. We're going to hear about Hyrax. Oh, before I forget, let me share the slides in case anyone would like. Go. Yeah, so let's go ahead and get started. Just a few announcements at the beginning here, and then we will have a presentation and demo from Aritra on Hyrax, which is a package for a machine learning package to enable discovery in the Rubin era. Aritra is a LSST Catalyst Fellow at University of Washington and the Dirac Institute. And we're very thankful to have you here. A couple of quick announcements before we get into that. Reminder that the Rubin Community Workshop is coming up at the end of July in Tucson. If you're interested, registration is open. I think it's filling up pretty quick, and there is a hard limit of 250 in-person attendees. So if you're interested, do register for that. There's a note here, a link here to a press release about installing the LSST camera, which was a few weeks back. Note also that you have until the end of the month if you wanted to provide input on community filters for the Antares broker. I think that all that requires is a brief description of what you're looking for, so it's not too onerous an ask. So do reply to that if you're interested. Next week's Science Assembly will be a drop-in discussion Q&A session. So if you're having any issues or questions, just want to discuss science or whatever, pop in. And then the following week, we will have a presentation on a recently submitted paper that used the Preview 0 simulated data set to make predictions for the detectability of satellite galaxies around the Milky Way. So that should be an excellent presentation as well. Oops, sorry, my thing is not working. As usual, we want to remind you that the Users Committee is a committee of 12 people listed here at the bottom, who are there to listen to your feedback about the Rubin data products and the science platform. So, so if you have anything you would like to raise to the users committee, there's information here about how to contact them via the community forum or an email or Google form. So they are there and welcome your feedback. I'd also like to highlight the weekly Link Frameworks office hours. If you're using any of the Link Frameworks tools, these open office hours are a place for you to get support or ask questions about those. So these are most Thursdays at 10 a.m. Pacific. And there is just a set of links here for those of you who are new. I shared the slides, so these are available to you to get started with the Science Platform account, resources on the Data Preview 0, and looking forward to the upcoming Data Preview 1. And with that, I'm going to keep it brief, and we can move on to a demo and presentation from Aritra. Ghosh, thank you so much for being here. I'll turn it over to you.
Thank you, Jeff. Hello, everyone. As Jeff said, I'm Aritra Ghosh. I'm a Catalyst Fellow at the University of Washington. And my scientific work is mostly with galaxies and AGN. But today I'm not going to be talking about most of them. And I'll be talking about some software work that we have been doing at the University of Washington. And this work I have been doing in partnership with Link Frameworks. The office hours that Jeff was advertising is relevant for this as well, in case whatever I show, you try to use it and have trouble later on. Those office hours are a very good resource. We usually have software engineers staffing those office hours who can help you with using these things. So the first what I will do is I will start with the presentation, and then I will move into like a demo trying to show you what this framework that we are building, what it does. So let me share my screen and we can get started. Okay. Okay. Can you folks see my screen? Yes. Okay, great. So this is the framework that I'm going to be talking about is called Hyrax. Actually, this was called FEBAD before. That's why on Jeff's slides, it said FEBAD, and one of the kind of the projects that Link Frameworks has, we changed the name only this month. What Hyrax is, it's like a framework for scalable machine learning and unsupervised discovery. What do I mean by that? So if you have done any machine learning project in astronomy, this is the typical workflow that it involves. You go to your whatever survey that you're using to get your data. These can be either you're trying to get co-added images, or you're trying to get difference images, you're trying to get spectra or light curves, any modality of data. You use some kind of source catalog that hopefully the survey has provided to you. You identify sources of interest, you download the data. These can be images, spectra, light curves, whatever you want to work with. Then the second step usually involves some kind of data cleaning or data processing. So essentially, you are using some kind of tools or a variety of tools to clean and pre-process that data. And the last, not the last, but kind of one of the most important tips is you build some kind of science model. And because I'm talking about machine learning, I'm assuming this runs on a GPU or could also run on a CPU. But it takes your data, makes some outputs. Then you go and manage, collate, and process those outputs that you have produced, make some plots, and hopefully write a paper. So this is kind of the generic workflow of a machine learning project in astronomy. But in this steps, what you, and I'm pretty sure if some of you have done this, you will know that many of these steps involve coding effort or doing some kind of software / codings that is beyond the typical astronomy training which graduates or undergraduates receive. For example, these, when you're dealing with data sets of the size of Rubin or Euclid or Roman, essentially the things that you have to care about, for example, are efficient loading of large numbers of tensors. If you have hundreds of thousands, millions, hundreds of millions of tensors, then if you're trying to train a model or something, how do you load them? How do you distribute your task across multiple GPUs? How do you perform like similarity searches, or you visualize the latent spaces of the models that you're building? And also this generic thing of scaling from laptops to high performance clusters to the cloud, that you want to have some kind of a framework which works across all these different hardware modalities. And currently the solution is that each research group kind of develops its own bespoke pipeline. And then the problem with that effort is often that you have to, for example, from speaking from personal experience, for example, working with undergraduate students, for example, right when you have trained them enough in order for them to kind of do the science in these machine learning projects, often it's time, the end of the summer, and time for them to move on. So this is kind of meant to take care of this long-running problem where what can we do to kind of stop writing, reproducing just the same work. So in order to tackle this, what we built is called Hyrax. It's called a framework for scalable machine learning, unsupervised discovery in astronomy. It's not an acronym. It's just named after this cute animal. And what Hyrax does, to kind of explain very succinctly, is in a machine learning project, you are kind of doing all these different kinds of tools. What we want you to do is just focus on writing your machine learning code, which is just one small piece. And what I mean by writing machine learning code is we want you to write your model. So whatever model that you want to use, whatever model that we want to build, you just focus on writing that tiny piece, and Hyrax takes care of everything else for you. How does it do that? It does it, so I explained these kind of 4 different bottlenecks, and what Hyrax does is essentially it has 4 different modules which takes care of each of these bottlenecks. First is what we call Hyrax download. So essentially, this is a download script slash workflow, which kind of goes on and gets you data from different kinds of servers. So we have tested this currently on HyperSupremeCam and Rubin. So those are the 2 data sets that we have actively tested it on, but you don't really need to use our downloader to work with any of the data. And what I mean by download is like data access, not necessarily download. So you might not be, depending on the survey, you might not be getting the data on your laptop. For something like Rubin, it means working on the science platform and just loading the data into your session, so as to say. Then we go have a prepare step. What prepares does is it kind of prepares the data to be trained. So this there's a lot of stuff happening under the hood, but it involves essentially efficiently loading the tensors. It's fast and parallelized, just like the download mechanism. And once you're done with that, you go to train. In training, we support the different popular machine learning libraries which are out there. And as I said, you don't have to care, you don't have to kind of worry about it. It automatically distributes your workload across all the GPUs that you have access to and everything. And at this point, the kind of pipeline splits into 2. You have a supervised framework and an unsupervised framework. So if you're doing supervised machine learning, in which you are trying to predict, let's say, classifications or other kinds of things based on training data set, in that you just run infer, which is just to infer on the data set that you didn't train on, and then you're done. Now, in terms of unsupervised learning, where you didn't provide or you don't have training labels, but you are trying to still use some kind of algorithm to cluster your data or to explore the latent space of your data, you run infer, and then we give you 2 tools in order to explore that latent space. One is we give you this tool called index. What index does, it essentially builds up a vector database, because in any unsupervised algorithm, what you're doing is you're taking some high dimensional space, which can be images, spectra, or whatever, and you're encoding those high dimensional objects into some lower dimensional latent space. Let's say you took 200 by 200 pixel images and encoded them into like a 50 dimensional latent space. What index does is it takes all these vectors, which let's say are just dimension 1 and has 50 length of 50, and builds up an efficient database of them. And then it puts the essential thing it does is that it does some computation on the back end, so that now if you want to do a similarity search, that you want to provide it an image and ask it, okay, give me all the images that look similar to this image. These databases kind of do that quicker than you trying to do that manually on your own if you were trying to work, like write a manual script in order to look up similar vectors. So that's what the vector databases do. They give you an efficient way to search these latent spaces. And the last one is this cool tool called Visualize. And what Visualize does is, again, it gives you an interactive tool to work with those embeddings or latent spaces, that it gives you a tool to quickly visualize and see what's going on in that latent space. What we are doing with Hyrax, as I kind of said, this is one of the Link Frameworks project. I have been doing this with the entire Link Frameworks team. If you don't know, Andy Conley and Rachel Mandelbaum are the 2 PIs of the Link Frameworks team. And I have been doing this, leading this project with Michael Tarasso and Drew Oldag, who are software engineers at the University of Washington. We have kind of picked 4 or 5 different projects to test Hyrax on, all of which are in this beta testing phase, where we are trying to get rid of all the bugs. And what I am primarily working on the first project mentioned over there. And then we have different teams spread across primarily University of Washington and Carnegie Mellon, where people are kind of testing out different things that they want to do with Hyrax. I will just this is the demo link we'll be using in case people want to follow along live. But let me finish this up first, and then we'll go to the demo. What we picked as the first kind of project to do with Hyrax is we took this data set of 100 million sources in Hypersupreme Chem wide. So this is GRI band data, all extended sources up till Redshift 1 and going down till 23rd magnitude. And what we did with Hyrax is essentially we built this using this suite of different deep learning algorithms. We kind of built a different kind of latent spaces with these 100 million cutouts. And what you can try to think of then is if you have a way to quickly generate these latent spaces, then you can kind of average over them or try to find out common spaces in between them to do like a whole host of different kinds of things. The things that we are focusing on is identification and subcharacterization of mergers, identification and characterization of low surface brightness features, image similarity searches, and also finding rare objects. And this one, when I say rare objects, I'm not talking about transients, but just rare static objects. So dual AGN ring galaxies, strong lenses, which have been missed by supervised finders, that kind of things. As I kind of indicated, Hyrax is in its kind of beta testing phase. It's public. You can go ahead. It's all out there. You can go ahead and use it. The only thing is it's not stable in the sense that we do make breaking changes fairly regularly. But after this summer, hopefully close to when DP1 or maybe a month or two after DP1 happens, we expect to have our full stable release so that after that we can guarantee some stability of the framework. If you have a project which you think will benefit from using Hyrax, you can either come find me. I am in the LSST Discovery Alliance Slack. So you can come find me there. You can go to the link office hours, or just if you scan this QR code, it will take you to a Google form. And we can also let you know once we have a more stable release for you to use. That's the talk portion or the slide portion of the presentation. And now I will move to the demo side. So let me stop sharing my screen and I will
We take a brief pause for see if anyone has questions before you move on. Thanks. Yeah, Valerio.
I have a question about the link that you provide in the slides. I will put it on the chat.
Sure.
Try to go there, but I couldn't reach it. Is that the correct link? Am I doing something wrong?
I got onto it.
Let me post in the chat. Oh yeah,
It's
you
an
do.
underscore.
Oh, okay, underscore.
I don't know. Yeah, the link worked for me.
Yeah, the link which you have, Valerio, in the chat, that seems to work for me as well. I don't know if there's some firewall or other thing happening.
Yeah, there's some like terms of service thing that popped up when I clicked it but if you accept that, then it worked fine.
Okay.
Sorry, it's still not working for me. Perhaps I live in Brazil. Perhaps there is problems with accessing a US site. I'm not sure.
Could be.
Unfortunate.
What I will do quickly is you might not be able to play around with this in real time. But I will just upload this file to the chat, and that way I don't know if I have a way to upload files, but I will provide this to Jeff at the end of the talk, and maybe Jeff can circulate it to you and others as well.
Yeah.
Okay. Thank you.
Any other questions before we have a demo? All right, I'll let you proceed then.
Okay. So, So I already ran these installation and import steps in the beginning. But what we'll do is the installation and imports are pretty similar. You just pip install Hyrax. I am doing this step of installing something called ngrok, but this is very specific to Google Colab. If you're not using Google Colab, for example, you don't need this. Then you just import Hyrax, and I'm importing some other things which will help us do this demo. And then the first step is downloading a small HSC dataset. So what this dataset is this is just a collection of 1,000 images from HyperSupremeCam wide, and these are in the redshift range 025 to 050 and magnitude less than 23. And the primary reason we are using HyperSupremeCam over here, I'm pretty sure as many of you know, HyperSupremeCam uses largely the same pipeline that LSST is going to use, or not similar, but similar, older version of the pipeline that LSST is going to use. So let's go ahead and download this data. So once you have this data, the first step to using Hyrax is creating this thing which is called an Hyrax object. So you just essentially, you can think about this as creating like a little bucket in which you will put all your little variables in, and then you'll run it. So what you do is called Hyrax, and then it creates this object. And then, because we put this object in this variable h, what we'll do is you will use this thing called config to kind of specify the different parameters that we want to use in our training. So as you can see over here, I have specified a dataset name, HSC dataset. I have specified the model that I'm trying to use, and I've specified what split between train test I want to use. And this data directory is the data directory where I just dumped all my downloaded images. Now, you will see that here I've specified Hyrax autoencoder. Now, this is a model that we already build within Hyrax. That's why when I specify just the model by name, it works. But this is not a requirement. You can kind of go ahead and kind of define your own model, and I will just do that in the notebook a little while after. So essentially, you set up all these config parameters, and once you have done, you just call train, and that's it, pretty much. It goes ahead, as you saw. I didn't specify it, but it goes ahead and tries to find whether you have a CPU or a GPU, or if you have multiple GPUs in your environment, it goes ahead and use it, and then you should have a model trained in a little while. So we'll just give this a little bit of time for this model to train. In Google Colab, I have found, I don't know, again, a weirdity of Colab. There's usually a progress bar as well. If you're working in your local environment, you should get a progress bar to keep track of your training. So the training finishes. This is, of course, a very simple model. That's why it trains so quickly. But then what we have is, for example, we have this tool called TensorBoard built into Hyrax. And what TensorBoard does is essentially it keeps a log of all the models that you're training. So essentially, let's say if you care about, you might or might not care about things like this, but if you're working with very large data sets, you essentially do have to start caring about these things. For example, if you're caring about how much your GPU is using memory or what the loads on GPUs are, you can kind of look up your different runs and then just compare different things in between them. So this is, and also read times of files when you're loading the images and everything. In our experiences, these are the kinds of things that we needed in order to kind of build an efficient framework. But these are also tweakable. You can plot different parameters or whatever you want to do. Now let's come to the point of what I was talking earlier. In the last step, I used a predefined model. But let's say I don't want to use a predefined model, and I just want to use a kind of a custom model that I'm doing. All I do, so this, as you can see, I've defined a new model called trial autoencoder. And this is just normal PyTorch code. So along with defining the model, you have to define a few other things. So these are the two functions that you have to define in order for Hyrax to work. One is this function called train step. So you want to tell the framework, because all machine learning models at the heart of it, you have to define what happens during training. So essentially, that's one train step that you have to define. And then we have this function called forward. and all forward defines is what do you want us to do during inference. So essentially, you're giving us two functions. One is train step and one is forward, which tells Hyrax what to do in terms of during model training and during inference. And in order to get all the kind of Hyrax powers, all you have to do is put this model decorator at the top. So you just, before you write your model, you just declare @Hyrax model. And this kind of goes and registers your model into the little framework, and then everything works perfect. So let's go ahead and define this model. And then what you need to do is then you just tell Hyrax, okay, what are the new config variables? I changed the model name to trial autoencoder because that's the name of this model that we just defined. And I specify the different loss functions. I specify what optimizer I want to use, the parameters of that optimizer. And just to note, we support kind of any optimizer or any criteria that PyTorch supports. So it's flexible to the extent of PyTorch. We go ahead and let's run this. So this again, I have already called train here. So it will go ahead and train this new model for us. Give it a few seconds to finish training. And this is kind of meant to be why it is useful is because if you're not using something like this, right, like getting to the point where even you have models which are training efficiently, it's non-trivial, so as to say. Now, what happens is I have, now this is, if you're trying to follow along this live, this step might or might not work for you, depending on whether you have done the ngrok step. If you are doing this within, as I've said, this is kind of only needed in Google Colab, and this might not work if you have not registered in ngrok and other things. But without Google Colab, if you're doing it any other just normal notebook, this will not be a problem. You just skip the step, and MLflow should load. Now, what MLflow is again very similarly, as these are the last two models that we train. These 54 seconds ago, 4 minutes ago, these are the latest two models that we trained. And for example, if you want to compare different things in between these models, there are a couple of ways to do this. First, let's say I want to look at what was the validation loss achieved by both the models, the training loss achieved by the models, what kind of learning rate was I using, and what kind of batch size was I using. So these are hyperparameters that typically have to tune. And these are the variables that are kind of the loss and other things that you kind of register. And if you go in there, you can see, for example, what are the different values of the loss functions that was achieved for the different models. So this is meant to be a quick way for you to test different implementations. There is another way to look at it. Instead of looking at a table, you can also just change it to a graph. So let's say I wanted to look at the training loss. I could expand this curve, and this kind of gives me for many of all my different models, how is the loss function decreasing over time and what I'm getting. So essentially, it gives you the things that you usually need to compare machine learning models and to do it quickly. So that is MLflow. MLflow is one of the tools that we have. Now, after you have gone ahead and defined your model, and also just to show you another piece, let's go ahead and actually rerun our first model. So this was our first model. Let's quickly rerun this. And you will see that you don't have to kind of keep opening up MLflow or anything. It just registers. I'm just doing this new training, and it will automatically just register this new training as well without us having to do anything. So let's just see that in action once. Give it a few minutes, few seconds rather. Okay, that finished. And now if I go to my little MLflow box, yeah, as you can see, it's still, it will register in a few seconds, but yeah, as you saw, that changed in kind of real time. As you, like, models usually train for hours, not seconds. So my point being that even when the model is training, you can come here and it will show you live statistics from the model as it is being trained. So that's all model training and the different comparison tools that we have. Now is inference. So once you have built your model, the next thing you want to do is inference. And we are building an autoencoder. And what autoencoders does is it takes images and kind of squeezes them into a smaller latent space and the hope is that similar objects are clustered together. And now you will see I'm defining, in order to run inference, again, I'm defining some of the config parameters, and all I will do is called infer. And what it does is it takes the latest model that we just trained, and then it will go ahead and then pass all the data that we did not use it. No, this is, we are passing just all the data through the framework, and then it tells you that it has saved the results at in some file. And what you need to do is the next step that we'll do is called visualize. So what we want to do is kind of visualize and take a look at this latent space. Now we have two latent space visualization tools built into Hyrax. One is a 2D visualizer and one is a 3D visualizer. Now, before doing the visualization, we'll use this tool called UMap in order to take our latent space and put it into a lower dimensional projection. So you run UMap, it does the work of making that latent space for you. And once you have done that, you use this tool called Hyrax Visualize in order to take a look at that latent space. Now here again, this is a Google Colab weirdity, which I'll explain to you in a second. This does not work on Google Colab, but again, on normal notebooks, this will work. And I will show it to you in a second that it works. This latent space is the collection of the different images that we had. And what you can do with this latent space is you can move around, you can like zoom in, zoom out. For example, if I want to take a look at these few points, I can just zoom into these points, and then this won't work here, but you can typically select these points and it will show up the object IDs as well as the different images. This is what it typically does. This is just a notebook I'm running locally instead of Google Colab. This is a different latent space. But what this does, for example, this is my entire latent space. Let's zoom into a little portion of it. Let's say I want to just go over here. So I go over here, and let's say I want to select only these objects, which are over here. So when you do that, what it does is it kind of shows you the different, you have to define what properties you want to see. I'm just showing some very trivial properties, nothing interesting. And it loads up the images that you use during training, and then it shows them to you. And you can, if you, for example, select a larger collection of points, you can also, because there are more points than the number of things, you can also resample from these points to see what kind of objects are being put over here. And this won't, the model that we just trained has 1,000 images, so it won't work in that sense, but it's just meant to be a demo to show you what it does. We also have a 3D latent space visualizer, and this cannot be used within a notebook because this uses some tools that are harder to kind of display within a notebook environment. But the instructions to use this are on GitHub. But what it does is, let's say you want to load up a JSON file, which has the latent space. You can create these JSON files using Hyrax. And this, instead of a 2D, this is just a 3D version of that latent space that we are trying to visualize. And what you can do, and this is just a demo of kind of why these visualization toolkits are important. This is a latent space of images, right? Of extragalactic sources. I personally am most interested in the structure or what is going on in these galaxies. Are there mergers? Are there low surface brightness features? Are there tidal tails? Those are the kind of questions that interest me. Now, if I want to see what this latent space has been ordered by, what I can do is let's try to color the points by magnitude. So this, as you can see, these are now colored by magnitude. Let's change this color scale to something more, which gives us kind of better visuals. So as you can see, this latent space is completely colored, it seems, by magnitude. And that for us is not really helpful. If I'm trying to figure out what I want is galaxies with similar structure to be clustered together. If they're completely sorted by magnitude, that is helpful to some extent, but not a lot. So this is meant to be kind of a tool of how you quickly run these latent spaces, and then you try to see whether this is useful or not. And then you go ahead and take design decisions which help you kind of build better latent spaces. In order to investigate this latent space, what we can also do is, for example, go ahead and select a part of it. And what that does is, again, builds up, let's say I want to also look at their magnitudes, their photo Z's, like whatever parameters that you are able to provide to the latent space, it will build up, it will show you all the objects that you selected. And again, over here, it shows you the images of the different galaxies that you use during training, for example. This is, again, I said, this is just a demo. These are just the same object, but you're just seeing how it was shredded by the deblender. And that's why you're seeing so many different objects within that bigger object. But this is, again, this is how you kind of explore these latent spaces and see whether your model is doing anything useful that you want it to do. Okay, now let's go back to the notebook. And after, let's say you have built this latent space, let me show you the vector database thing I was talking about. So h.index, what that does is then creates that vector database. So let's go ahead and quickly do that. So what this will do is create that vector database off with those different vectors. And let's say this little code over here kind of builds up a way for us to connect to that database. And let's say we want to search, this is just for demo purposes, I see pulled up a random object ID. I want to see all the objects which are kind of closest to this object ID. Kind of gave me 5 answers. Let's go ahead and actually take a look at these objects. Okay, so this is the original search object that I used in order to search. And this is a small data set. Most of the galaxies are featureless, look like this. And these are the objects that it pulled up. So this is the closest neighbor. And then as you go further and further, there's more nearest, more further away neighbors. And as you can see, all these are kind of pretty small featureless galaxies that kind of pulled out of the vector database. This is an uninteresting demo, but for example, if you were to pass it mergers, if you were to pass it things with tidal tails, it should go and build, depending on how you have built up your latent space, it should go ahead and pull out those objects for you. So that's it. That's all the demo I had, and I am happy to take more questions.
Yeah, I see a question from Luis.
Hi, Aritra. That was really wonderful. Thank you. Hello. What is the difference between the 2 models that we trained that were in the demo?
I just put in a trivial difference in between them. I just changed the sizes or the thing of one of the layers, but it was just to show you what happens when you train 2 different models. There's no inherent difference in between them, except just a change in size somewhere in the model.
Okay.
But you're not limited to either these models or these kinds of models in any way. You can just go ahead and train like convolutional neural networks or
Right,
any
whatever.
other kind of thing that you want to do.
Okay, great. Thank you.
Yeah, Bob.
Thank you, Aritra. Hey, could you provide a link to some more documentation? I'd like to read some more about this.
Yeah, let me this is the GitHub repo. Let me see if we have the docs linked over there. We might not. Let's see.
Okay, good.
And this is the read the docs. The only thing I will warn again is we are going out and doing these demos now to have more feedback from the community. But the docs, as you might see, are pretty thin at this point. And we are hoping by August and September, these are better, and we should have at least a couple of things out, which should make it more accessible to users.
Well, this will get me started, man. I appreciate it.
Yeah, Louise.
Another question. I'll let you read the question in the chat. It's the exact same question.
Okay. Yeah. So with the RSP, we have tested this out on the USDF RSP, so the non-cloud RSP, not the cloud RSP, but the USDF RSP. And it works because it's just because it works in any, it's just a pip module, so you can just install it and make it work, and it works out of the box. We have installed it on the public RSP as well, but we have not played around as extensively with it on the public RSP. Our hope is as DP1 happens and we will kind of play around with it more. And some of the tools we might have to work closely with the team which maintains the RSP in order to have some of these visualization toolkits working there. Because there might be some issues. I know Firefly is natively supported within the RSP, but in order to get some of these port forwarding and other things working, we might have to work closely with the RSP in order to get those working. So that's kind of, yeah, we are testing it out, but not fully on the public RSP yet.
As a follow-up, are there concerns, I guess, that users have a limited container size when they log into the RSP? Does that present issues, I guess, then with trying to use Hyrax?
Yes, there's a couple of issues, and I know this is kind of a Rubin level question that has not been, we have not achieved a solution yet. Yes, the same GPU is the next question is, I know there's the time or resource allocation. I remember at the last community workshop, there's some conversation about how resource allocation would happen, or there would be a committee in order to allocate resources for people with bigger requests. In terms of GPUs, there's a couple of answers to this. So what we hope is, even if they're not GPUs, there are no GPUs on the RSP going forward, that there would be GPUs at least at a few IDACs, and then we'll work closely with the IDACs to deploy the same thing on those IDACs. And the second thing is, you could imagine where especially we are kind of, it seems that some people are moving towards a part of the community is moving towards building these larger models, which kind of builds these latent spaces. And then what you can imagine is, let's say, if someone provides a latent space of all the DP1 data, let's say, or when DR1 happens, and if that is provided to the community science team, in whether that at least can be integrated into the public RSP. And then even if you're not able to train like a giant model, if you want to just fine tune that model, even with CPU resources, there will be enough resources to fine tune that model. So that's the other approach, which is possible on the public RSP as well. And I think as we collect more feedback from users, and if all of you have ideas, please send them to me. We'll kind of stabilize on what's the current. And with DP1, I think it will be a nice thing to test out with real data to see how people are using it, and that will kind of inform us of what is the best approach forward, so as to say.
I was going to ask about DP1 actually, because it's really not a large data set. And so is it a useful data set for testing out how Hyrax and other machine learning tools like work? Or do we really need to wait for data preview 2 maybe?
I think the scientific value in these unsupervised tools, let's say, I think only DR1 will bring. DP1, I think, will be a good data set to, I think, especially because of the depth of ECDFS in DP1, this will be a good thing to test in terms of, at least if your science involves something that is only achievable at 10-year depth, then DP1 might be good to kind of look at least some of the fields which have been observed to larger depths to see kind of what can you get from these. But in terms of finding anomalies or rare sources, because it's only a few square degrees or half a square degree, yeah, it's not really you won't really get bang for your buck, so as to say, with respect to that.
Yeah. Any other questions? What we do, mentioned that you would share a rendered version of the of that demo. If you're okay with it, we could share that on the as a reply to the community forum post announcing this event. Super. That way it'll be there for people to refer back to. All right. Well, if we don't have any more questions, maybe we all just want to go off and experiment now with with Hyrax and learn how to use it. Thanks so much, Aritra. This was really great, and thank you all for being here.
Thank y'all. That was great, Aritra.